So we're continuing with Taylor polynomials and of course Maclaurin polynomials. So if you have a Taylor polynomial, p sub n of x, and you use it to approximate a function's value, f of x, it'd be nice to know how good an approximation it is. Sort of like we know with the alternating series test that if you add, say, the first 6 terms of an alternating series, that your error is less than the absolute value of the, sorry, did I say 6? I don't know how many I said, 5, then the error is less than the absolute value of the 6th term. So what we're going to look at today is, how can we do something similar, not quite the same, but actually it's very similar with Taylor polynomials. So f of x is the exact value. P sub n of x at some point is the approximation, and r sub n of x is going to be your remainder. Okay, so the remainder, its absolute value is called the error. Okay, some people think remainder and error are exactly the same. Not quite, because the remainder could be negative. But the absolute value of the remainder is the error, and that's the difference between the absolute value of f of x and p sub n of x. You'll sometimes see this in questions, especially on the AP exam. They'll ask you, find an approximation for the absolute value of f, whatever the function is, minus whatever the polynomial is at a particular point. Okay, so to do this, we use something called Taylor's formula or Taylor's theorem. It's sometimes called the Lagrange form of the remainder. And it says this: if a function f is differentiable through order n plus 1, so it just needs to be, if we're doing the first 5 terms, it needs to be the 6th derivative needs to exist in an interval I containing c. So in this interval containing wherever we're centering our approximation, then for every x in that interval I, there exists a number z. And you're like, oh gosh, more letters? Yes, there exists a number z between x and c such that f of x is equal to p sub n of x plus r sub n of x. That's just the, the value of the function is equal to the polynomial plus whatever remainder, where the remainder is equal to the n plus first derivative at z over n plus 1 factorial times x minus c to the n plus 1. Before we go on to anything else, let me just point out that if this was the n plus first derivative at x over n plus 1 factorial times x minus c to the n plus 1, this would exactly be whatever the next term was. I'm sorry, if this was a c instead of z, right? That would just be the next term, okay? If it's an alternating series, we can just use that next term. But if it's not an alternating series, then we need to figure this part out. Now, in point of fact, we will pretty much never figure out what z is. This theorem simply guarantees that there exists a z that's going to make the remainder exactly equal to this. And that z is somewhere in the interval I. Okay? So what we do then is we say that the absolute value of the remainder is less than or equal to, and this is the way most books write it. I wish they just put the max value of f of n plus 1, f to the n plus, f super n plus 1 of z, and put that here, because that's really where it belongs, over n plus 1 factorial times the absolute value of x minus c to the n plus 1. So basically we're taking the absolute value of all this stuff, where the maximum of the n plus first derivative of f at z is the maximum value of the n plus first derivative between x and c. Okay, so x is where you're trying to evaluate it, and c is where you're centering it. So that's the interval we're going to look on. We're going to look to find what's the maximum value of the derivative, whichever derivative we're on, in that interval. And we're going to use that for our numerator here instead of the n plus first derivative at our centering point c. Everything else is just the next term. All right, so for example, sine of x can be approximated by p sub 3 of x is equal to x minus x cubed over 3 factorial. So first, use p sub 3 of x to approximate sine of 0.1. I'm just going to stop there and do that. So sine of 0.1 is approximately equal to p sub 3 of 0.1. And I'm always really careful to make sure to say that's an approximation. It's not exactly this, which is going to be equal to 0.1 minus 0.1 cubed over 3 factorial, which would be, let's see, that's 0.1 minus 1/1000th over 6. I have no idea what that comes out to be as just a number, so I'm going to grab a calculator and go, okay, yeah, what is that? So 0.1 minus 0.001 divided by 6 is 0.09983 repeating. So that's the approximation for sine of 0.1. And it's no surprise to us that it's close to 0 because sine of 0 is 0. Then use Taylor's formula to find a range of possible values for sine of 0.1. Okay, so what I'm going to do is go back up here to this and say, okay, the absolute value of the remainder, so the absolute value of r sub 3, because we're using a third degree polynomial, of x is going to be less than or equal to the maximum value of the fourth derivative of sine of x so I'm going to say just the fourth derivative over 4 factorial times the absolute value of x minus c to the n plus 1. So x minus, where are we centering this? Oh, we're clearly centering it at 0, right? Because there's not an x plus 3 or an x minus 4 or something like that to the 4th power. So the absolute value of the remainder, r sub 3 of 0.1, is going to be less than or equal to, you can look at what is the fourth derivative of sine and then look between x is 0 and x is 0.1, right, between c and where we're actually evaluating it, and find the maximum value. However, one of the nice things with sine and cosine, for that matter, is the maximum value of any derivative on any interval is going to be 1. So this is going to be 1 factorial times 0.1 to the 4th power. So that's 0.0001 over 4 factorial, which is 24. And that 0.0001 divided by 24 is tiny. 0.12345 zeros, 416 repeating. So when they ask you to find a range of possible values, what we can do is our range, it's a little bit like, remember when we did confidence intervals in statistics? We found where, our sample said that everything was, and then we found how much error there could be, and we added and subtracted that. It's just like that. Our range of possible values is going to be 0.09983 plus or minus our 0.000000416 repeating. So if we're given a range of possible values, if we subtract those two, we get that it's on a range of 0.099829116 repeating. And if we add it, it's 0.0998375. So we know that the true value is going to fall somewhere in between that, which is the difference between math and statistics. With confidence intervals, we would say things like, we're 90% confident that the actual value lies in between these two. Here we're completely confident. The other thing to notice about this is, well, this is an alternating series, right? If you're doing the series for sine, it's going to be an alternating series. Now, your book will actually, on this one, I don't like the way that they do it. If I remember correctly, they will say, well, since the series really, if you actually did the series, it wouldn't have a fourth degree term. They would take the fifth, and I'm like, that's not what the theorem actually says, so I don't like that. Okay, the nice folks at the College Board are really good at avoiding things that might be taught differently in different textbooks. All right, so let's try this one. Let's determine the degree of the Taylor polynomial expanded about c is equal to 1 that should be used to approximate natural log of 1.2 so that the error is less than 1/1000th. Okay, so if we start looking at the Taylor polynomial for this, our function f of x is the natural log of x, and we're going to center this at c is equal to 1. So f of 1 is the natural log of 1, which is 0. Then f prime of x is x to the negative 1. F prime at 1 is 1. F double prime of x is negative x to the negative 2. So f double prime at 1 is negative 1. The third derivative of f at x is going to be 2x to the negative 3. So my third derivative at 1 is going to be positive 2. And I think you can start to see that there's a pattern that's emerging here, right? The fourth derivative, we'll go ahead and do that one, f super 4. is going to be negative 6x to the negative 4. So the fourth derivative at 1 will be negative 6. Now, why this is important is because we need to have some sort of an expression for the nth derivative at 1, or the nth derivative at all. So f super n of x is going to be equal to, well, first of all, we notice that this is an alternating series. These are alternating, right? 1, -1, 2, -6. So that's going to be -1 to the, at the first derivative, it's positive, right? In the second derivative, it's negative. So I'm going to raise that to the n plus 1 power. So it alternates and starts off positive at 1 and then negative. And then the value, these numbers are always, if I take one less than the derivative and do a factorial, that's what I have. So that's going to be n minus 1 factorial. Okay, so our error is equal to the absolute value of r sub n of x. And we know that that absolute value is going to be less than or equal to the max of the n plus first derivative at x over n plus 1 factorial times x minus 1 to the n plus 1 power. And we want this to be less than 1/1000th. All right. So if we looked at oh, sorry, I left off the last part of this. Times x to the negative n power. Okay, so we're going to look at, on the interval from 1 to 2, or 1 to 1.2, right? Because 1 is where we're centering it, and 1.2 is what we're trying to evaluate. If I make x 1, that's going to make this derivative as large as possible, because if I make it 1.2, we'll have a larger denominator, right? So that'll make it smaller. So that part's just simply going to drop out. So this is going to be less than or equal to the maximum value, and all this is, if we go back up to the formula, it's the maximum value of the absolute value, right? So I don't have to worry about the negative part, about the alternating part. And this, to make this as large as possible, I need to put in 1, so that's just going to be 1. So that's simply going to be n minus 1 factorial and what's on bottom will be n plus 1 factorial. We're evaluating this at x is 1.2, so this will be 0.2 to the n plus 1 power. So at that point, what we really want to do is go, okay, we could do guess and check to figure it out, but let's grab a calculator and do that. So in y, I'm going to put n minus 1 factorial, so x minus 1 factorial over x plus 1 factorial oops, forgot the parentheses. Oh, and I do need to make a quick correction here. So this is supposed to be the n plus first derivative. So that means this is going to be n factorial because it's n plus 1 minus 1. And then that'll be times 0.2 to the n plus 1. So I need to go back and fix this. Delete, delete. Point 2 raised to the x plus 1. And I probably should have, I wasn't thinking about it, simplified this just to 1 over n plus 1 times 0.2 to the n plus 1. In any event, if we set up our table to go by ones, it's probably already set. Here we go. So we want n to be equal to 3. So that was the first one that was gave us a value that would ensure the error would be less than. So we would need 3 terms. Okay. All right, let's go on to some AP problems that I pulled out. So let's look at this one. Let h be a function having derivatives of all orders for x greater than 0. Selected values of h and its first 4 derivatives are indicated in the table above. The function h and these 4 derivatives are increasing on the interval from 1 to 3. Well, that's an interesting thing to throw in there, but okay. Find the first degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. Is this approximation greater than or less than h of 1.9? Explain your reasoning. All right. So anytime they get to an and, I stop before the and I'm like, I want to make sure I do that. I want the first degree Taylor polynomial. So I want t sub 1 of x or p sub 1 of x. It doesn't really matter which. We're evaluating this at about x plus 2. So it's going to be the original function, 80, plus 128 over 1 factorial, so that'll be 128 times x minus 2. A first degree Taylor polynomial is the tangent line approximation. It's just point slope. So h of 1.9 is approximately equal then to 80 plus 128 times 1.9 minus 2. If this were the AP exam, I would just leave it because, well, that's perfectly numeric. But I'll go ahead and work it out. This is going to be 80. That'll be negative 0.1. So this will be negative 12.8. So that'll be 67.2. So that's the second part, done this, done this. Is this approximation greater than or less than h of 1.9? Well, if we have a function that is increasing and its derivative is increasing, what does the shape of the function look like then?
It's just linear.
Oh, but the derivative is increasing also.
It's like quadratic.
Yeah, but it's just the increasing part, right? It's increasing concave up. So if I did a tangent line approximation, what do we know? The approximation is less than h of 1.9. Because h double prime at 2 is positive. All right, part B, write the third degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. You're like, okay, well, it's going to start off exactly the same way. T sub 3 of x will be 80 plus 128 times x minus 2 plus 488 over 3 over 2 factorial times x minus 2 squared plus 448 over 3 over 3 factorial times x minus 2 cubed. So then h of 1.9 will be approximately equal to, we already figured out these first two terms are 67.2 plus, let's see, that'll be 488. 2 factorial is 2, so that'll be over 6 times 1.9 minus 2 squared plus, this will be 448 over 3 factorial is 6 times 3 is 18 times 1.9 minus 2 quantity cubed. And I'm not so curious about it that I care to bother finding that value. All that is stuff that we did the other day with Taylor polynomials. Next, though, we want to look at, all right, part C, use the Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with error less than 3 times 10 to the negative 4th. All right, I'm going to delete all this stuff so that I have a little bit of room. All right, so we know that the error is equal to the absolute value of the remainder, and this is a third degree polynomial, so r sub 3 at 1.9 which is going to be less than or equal to, we want the maximum value of the fourth derivative on the interval from 1.9 to 2. Now, we know that h's derivatives are increasing. So the maximum is going to occur at 584/9 over 4 factorial times 1.9 minus 2 to the 4th power, and I'm going to slap absolute value around that whole thing. And I sure hope that that was a calculator problem. I imagine that it was. So let's see, 584 divided by 9 divided by 24 multiplied times 0.1 raised to the 4th. This is equal to 0.000, wait a minute, one too many zeros, wait. 1, 2, 3, oh no, that's right. 27, which is less than 3 times 10 to the negative 4th. This is actually, if I'd been thinking about it, this is 2.7 times 10 to the negative 4th, which is less than 3 times 10 to the negative 4th. All right, let's look at the rubric real quickly. I'm going to point out one thing to you where I had some sort of violent disagreement with somebody about it. So the first degree Taylor polynomial, we got 67.2, didn't we? Tell me we got 67.2. Okay, good. And they said h prime is increasing on the interval from 1 to 3. Did we say h double prime was positive?
Yes.
So we probably should have said it this way. I think we would have gotten credit because h double prime positive means that h prime is increasing by definition. Those are one and the same thing. Then they give the approximation here. It's exactly what we had, except they went ahead and put in the 1.9 and calculated it. This is the part where I strongly disagreed with some people, and I in the end, the rubric was the rubric, and so you didn't get a point, and I purposely didn't write it out. It says that as part of your reasoning, you had to explain why this was the maximum value of the 4th derivative. If you didn't do that, you lost one of these 2 points. And I was like, and they were like, well, how do you know they weren't just guessing? I'm like, well, they guessed the right one, and it doesn't say explain your reasoning. So I disliked that one. So we ended up with this, which is less than 3 times 10 to the negative 4th. Okay? All right, let's look at another one. I don't know how much time we have. This class is over at 10:50. No, we've got 2.5 minutes. Plenty of time. All right, so they want you to find the 3rd degree Taylor polynomial. That's not anything big, right? You know how to do that. We've done that multiple times. Find the coefficient of the 22nd, x to the 22nd in this series. That takes a little bit of thinking, but it's not all that bad. Here, this is what I was telling you about in the notes. It says use the Lagrange error bound to show that f of 1/10 minus p of 1/10 is less than 1/100th. Well, this is r of 1/10. Right? That is the remainder. So we're just using the Lagrange error bound. So what you would do is you would take the fourth derivative, because p sub 3 is the third degree Taylor polynomial, find its maximum value, and then divide that by 4 factorial times 1/10 minus 0 to the fourth power. So let me show you what they did since we're running out of time. So for the max value, they got 625, and you're like, wait a minute, it's sine. But yeah, every time we take a derivative of this, we get another 5 as a factor. So when we're into the fourth derivative, that's 5 to the fourth is 625. Over 4 factorial times 1/10 to the fourth ends up being 1 over 384, which is less than 1 over 100. All right. And I have about 30 seconds. They did also ask kind of an interesting question. G of x is the integral from 0 to x of f of t dt. Write the third degree Taylor polynomial for that. So what they did was they took the second degree Taylor polynomial and then integrated it to get the third degree Taylor polynomial. And that's because when you take the antiderivative, you go up a degree. Okay.